Recall that a living cell is a miniature chemical factory where thousands of reactions occur every moment of the day. Metabolism is the term that we use to describe the sum of all change occurring within an organism. These are reactions that build things up and break things down. Changes in energy that's acquired versus changes in energy that is utilized. Remember that one of our criteria of a living thing is that the organism or cell be able to use and obtain energy to keep going. If metabolism is the sum of the parts, metabolism can be broken down to describe catabolism and anabolism, the energy that's being acquired coming into the system versus the energy that's being utilized or being expended. The frog represents a node in the food web. Energy is ingested and utilized for metabolic processes and transformed into biomass. Energy flow is continuous on its path through the frog. And if the frog is ingested by predators, parasites, or decomposes, that energy can be acquired elsewhere. But as we are just starting out, our big focus will be on classifying reactions as those that give off energy or consume energy. And so we've already mentioned the terms anabolic and catabolic, but now we're tying them to energy. Endergonic reactions, think endo, within, are energy consuming reactions. The anabolic reactions consume energy because systems require energy to form bonds. Exergonic reactions, think exiting the cell, are energy releasing reactions. These are catabolic reactions that involve bond breaking, a big molecule being broken down into smaller and smaller bits. To understand metabolism, we have to lay a foundation within physics first. There are two laws in thermodynamics that provide context to this discussion. The first law is known as the law of conservation. Energy is constant. It is neither made or destroyed, but it can be passed, transferred, and transformed between systems. So like Newton's cradle here, the energy coming in from one ball passes through all the other balls in the center, and that same exact energy is exerted elsewhere. Another way to think or summarize the energy of conservation law is that for every action, there's an equal and opposite reaction. So if we can understand that energy is constant, but that it can change, we can recognize that there are stages of energy: kinetic versus potential. Kinetic energy is energy that's actively being used, actively in motion, whereas potential energy is energy that's stored. It exists, but it's not doing anything yet. So taking a look at these four scenarios, see if you can identify kinetic energy that's actively entering or leaving a state, and potential energy. When energy is being utilized or changing between systems, it's important to note that the energy can be converted from one form to another. We use the terms transferred and transformed to denote these changes. Transferring energy means we're just moving the energy from point A to point B. It's an interaction between systems where the energy remains the same, just moved. Transformation, on the other hand, forms a new product. The energy is changed in some way, shape, or form, modified. So to help illustrate this, we're looking at the water cycle here, and we can see that when liquid water is evaporated and formed into water vapor, we have transformation, we have changed states. Gaseous water vapor is also transformed when it condenses down back into liquid water. However, when that liquid water drops from the clouds onto the land surface below, we see transference. And when that water runs down the mountainside out to the ocean, we again see transfer. So taking a look at these practice examples, see through the story whether energy is just being moved from point A to point B, or whether the type of energy is changing. The second law of thermodynamics, also known as the entropy principle, states that some energy is unusable by that system and it will be given off as heat. The term entropy refers to disorder or chaos. And so the entropy principle describes how, left to its own devices, a system will naturally gravitate toward a more disorganized and chaotic state, and that it will require energy to bring it all back into order. So here we see that principle being repeated here. Left to its own devices, a system will become more and more disorganized. But by applying energy, we can return it to a highly ordered state. Understanding entropy allows us to manipulate this system. We know that if we increase the temperature, we can increase atomic energy. If we allow a larger volume of space, there'll be more energy within, because there's more chaos occurring, more positions that an atom could be in a larger space. If you're going through phase changes, you could increase entropy and chaos. If you are mixing multiple solutions together, more different particles means more chaos, more energy. And composition reactions. If you make bigger things, you're going to have more energy and entropy. So taking a look at these 4 scenarios and the stories they may be telling, determine whether entropy is increasing or decreasing. Let's revisit chemistry. Recall that all chemical reactions involve bond breaking and bond making. Oftentimes, these pathways are reversible. A pathway is really just a series of linked reactions leading from point A to point B, from a reactant to a product. It may not be one reaction long, it may be several reactions. How does one start a chemical reaction? Well, if every chemical reaction involves bond breaking and bond forming, we must first start with bond breaking. You have to release an electron so that way it's single and ready to mingle. It's available to form a new bond. This is known as the activation energy, the amount of energy required to break that initial bond. Where does that energy come from? Some atoms are inherently more reactive. Their electrons are more likely to dissociate. More often, the energy to disrupt bonds comes from atomic collisions, when they collide with enough force to break bonds. What you see on the right is what's known as the energy of activation curve. We see a small hump, that's the height required to break the first bond. And then the slope downward is the actual reaction taking place. This height may vary depending upon the type of reaction that's occurring, but in all cases, the initial bump is the energy required to break that first bond. Collision theory describes how chemical reactions occur when atoms, ions, and molecules collide with enough force to disrupt that initial bond. Understanding that means we can drive reactions to occur more readily by understanding ways to excite atoms. We can increase heat. The more collisions there are, the more likelihood that one of them will disrupt an electron configuration. But it's more than just urging atoms to collide. The reactants not only have to be moving with speed and vigor, they have to be facing in the correct orientation so that way when a bond is broken, they're also poised to make a new bond. Left to their own devices, considering that atoms move randomly and chaotically, reactions would not occur regularly or with any predictable certainty. This is where enzymes come in. Each step in a catabolic pathway is catalyzed, assisted by a specific enzyme. The word specific means it can only do this one reaction. So if we look at the bottom panel and we can see a chemical reaction pathway, starting molecule A can be changed and converted, transformed into blue squared B. There's an enzyme, enzyme 1, that assists in this initial reaction. In the meantime, enzyme 2 is sitting and twiddling its thumbs, waiting for there to be a blue squared B, And then it could assist in blue square B becoming a brown square C, and so on and so forth. Remember that form dictates function. And so understanding the shape and structure of an enzyme helps explain how it's able to do its job. The players in this reaction, there's the substrate, which is the reactant, the starting molecule, and the location that it's going to bind. We previously described how the term substrate is used to describe the location of binding, the location of a chemical reaction. Here we see that term can sometimes also be used to describe the starting molecule or reactant. And what we see is that the enzyme can bind to the substrate, forming what's known as an enzyme-substrate complex. It's an intermediate state where both enzyme and substrate exist simultaneously bound together. And then the reaction occurs, creating an enzyme product complex where the enzyme is attached to the product prior to release. This is able to occur because enzymes follow an induced fit model. The enzyme has a general shape that binds to the particular substrates or reactants that it is intended for, but then it can wiggle. There's a conformational change that allows it to better attach, to push the electron clouds together of those substrates or pull the electron clouds apart, straining those bonds, depending upon the type of reaction the enzyme has evolved to become. And by doing this induced fit wiggle, the enzyme allows the reactants to undergo their own chemical reaction and then releases the products. The contrast to an induced fit model with wiggle room would be a lock and key model, where there's a perfect fit and it slides in and out exactly. Enzymes are the hero of our chemical reaction timeline because they're able to speed up slow reactions. Taking a closer look at our energy of activation curves, we can see that the black curve is the standard energy of activation without an enzyme. But now we can see a red curve below it, a lower energy requirement when the enzyme is present. Note here that the reactants start in the same place and the products end at the same place. So the overall chemical reaction has not changed, only the amount of energy required to start it. We mentioned previously that enzymes help the body overcome the hurdle of activation, and they do this specifically by bringing the reactants together and covalently bonding them so that those reactants are held in place until the reaction has completed. They shelter those reactants, providing a favorable environment for the reaction to occur. Because of that induced fit, they can push the reactants together so their electron clouds can bond together in a synthesis reaction, or pull them apart to strain existing bonds in a decomposition reaction. Finally, when binding the substrates to the enzyme, they do so and orient the substrates correctly so that they are ready and able to bond correctly. Each enzyme in existence has its own optimal environment. This is based on the organism or organ it resides in and the type of work that it does. The term optimum means ideal, where it's going to work best. The diagram below describes terms that we use for different temperature ranges of bacteria environments. If there's such a thing as an enzyme's optimum, that means there are factors at play that can make an enzyme less reliable. Be aware of the different factors and the impact that they can have. One factor is substrate concentration. If you have too many starting materials, the enzyme becomes saturated, meaning all the enzyme's active sites are already bound and occupied, and the enzyme's maximum speed of reaction has been reached. And so the enzyme appears to plateau. What we can see in the bottom panel here is 3 enzymes are vastly outnumbered by substrates, and so the maximum capacity of this reaction hits a glass ceiling. This can be corrected for by adding more enzyme or increasing the temperature a little bit, because that will energize the enzymes so that they work a little faster. Speaking of temperature, environment is another factor that affects the enzyme's ability to function. Temperature specifically. If it's too cold, the enzyme becomes rigid, frozen, and its induced fit wiggle is hindered, so it's not able to work well. Too hot, and the enzyme's own bonds break, causing the enzyme to unravel, and then it cannot bond and hold fast to the substrates. pH can also affect the environment the enzyme works in. Either extreme, whether too acidic or too alkaline, will break bonds, also affecting the induced fit. This bond breakage leads to the loss of the three-dimensional shape. We refer to this as denaturation. Finally, enzymes can be affected by inhibitors. Inhibitors come in two forms: competitive inhibitors and non-competitive inhibitors. They get their name from where they bind to. The competitive inhibitor actively binds for the same site that the substrate will bind to, thereby competing for bonding. The non-competitive inhibitor will bind someplace else, but because of that induced wiggle, when the non-competitor binds, it changes the conformational shape, and so the enzyme might not be able to also bind to its substrate. If you're dealing with inhibitors, this too can be corrected by adding more substrate. In a situation where enzymes are outnumbered by inhibitors, or the substrate is outnumbered by inhibitors, the reaction will find itself coming to a halt. This can be corrected by either adding more substrate, which increases the odds that the enzyme will bind to the substrate, not the inhibitor, or by adding more enzyme. Inhibitors sound negative, but our body produces the bulk of the inhibitors, and this allows our bodies to have regulatory control over the reactions, ensuring that we're making what we need when we need it. Understanding this has led us to capitalize and pharmaceutically provide therapeutic enzymes to compensate and modify systems that are in disarray. Further study into enzymes and their inhibitors have revealed a feedback inhibition. Often, it is the product of the pathway that acts as the inhibitor. This allows the cell to regulate what it's making and prevent the cell from wasting chemical resources. Why make something if you are not utilizing it simultaneously? So in the panel that we have here, we can see a story where the substrate is going through intermediates A, B to the end product, and that end product globular red ball acts as the inhibitor, shutting it down, saying, you've made enough, we don't need any more. But the end product, spherical red ball, was created for a purpose. And so little by little, it's going to be utilized elsewhere in the body, decreasing the amount of end product available to bind to the enzyme and inhibit it. So at some point, there will be no more inhibitors, and this will turn back on the pathway to generate more of that perfect globular red ball.